Warm welcome to all my viewers. Today I am here to teach you the first chapter of physics, electricity. So let's go. I'll be teaching you what is an electricity, a charge and current and its SI units, and potential difference, then Ohm's law, and the last one is the circuit diagrams. So let's start with then electricity. What is an electricity? Electricity is nothing but flow of charges. Flow of charges means there are two types of charge. What are they? Positive and negative charge. Yeah, right? So next we'll keep on moving the charge. Charge can be also represented in the form of capital Q. Okay? And current can be also represented in the form of capital I. Now let's define current. What is a current? It is defined as a flow of charge across a conductor per time. So the definition itself derives the formula. If you read the definition again once more, you may take the formula itself from the words. So it is defined as flow of charge across the conductor per time. So per time here it means the time is in the denominator. So what will be in the numerator? It cannot be, it is defined as, okay, and across the conductor. That is extra information, right? So what is remaining over here? Flow of charge and per time. Okay, so we can derive the formula from its sentences itself. So the flow of charge will be nothing but the numerator. So flow of charge per time. Flow of charge per time. Now we have the formula over here. Now let's execute it in the words. Instead of, now here it is in the words. Now let's represent it in the letters format. So flow of charge is represented in the form of capital Q. So let's write Q, and current is nothing but capital I. Capital I is equal to Q by T. Now we can even find the formula what is equal to Q is equal to how much. So charge is equal to, so the Q will be back. Q is equal to I into T. I into T. Now we derived what is the value, how to find charge and how to find the current. Now let's find the SI unit of them. What is the SI unit of a charge if you ask? SI unit of a charge is nothing but a coulomb. Okay. And the SI unit of a current is nothing but Ampere. Okay, so SI unit of a current is nothing but an ampere, and the SI unit of a charge is nothing but a coulomb. Now let's define what is an ampere. We defined what is a current and we derived its formula also. Now let's derive what is an ampere. Okay, an ampere is nothing but it is the amount of current that flows when 1 coulomb flows across a conductor for a time interval of 1 second. So if you notice over here, I used here like 1 coulomb. 1 coulomb and 1 second. Why 1 second and 1 coulomb if you ask? It's because I am deriving the formula for an 1 ampere. I am making a statement for an ampere. I am not doing anything for like 2 ampere means I can even give 2 coulomb by 1 second. 4 by 2 is equal to 1. So the formula, let's derive its formula. An ampere. So ampere is nothing but the SI unit of a current. So a current is nothing but current is equal to Q by T. It's all in SI, it's not in the SI unit form, right? So let's convert into SI unit. So the SI unit of a current is nothing but an ampere. So let's write an ampere is equal to Q is nothing but the charge. Charge SI unit is nothing but a coulomb. So ampere is equal to coulomb by second. So the SI unit of time is nothing but second. So we have the SI unit, we need to find the formula for using the SI units, we just substituted using the SI units. Now let's check. Okay, this is the statement for an ampere. It is the amount of current that flows when 1 coulomb of charge flows across a conductor for a time interval of 1 second. Okay, now what is a microampere and milliampere? Sometime in the question you may get use the microampere, it's a microampere, it's a milliampere. So the value for a microampere is nothing but 10 raised to minus 6. Okay, 10 raised to minus 6 is for a microampere, and it is written as in the form of U like that. U shape, okay? Opposite U. I mean opposite Y or something, okay? So now what is a milliampere? If you ask, milliampere is nothing but 10 raised to minus 3. And this can be written as a small m and a. Okay? So this is the thing. Now let's check what is the potential and potential difference. The term potential and potential difference, you may think they have different meaning, but it's not like that. It is like they have the same meaning. The potential can be either set as potential different or potential. Okay, so let's derive it. So potential and potential difference is nothing but the amount of work done. Okay, the amount of work done to move one coulomb of charge from one point to another. So potential and potential difference is nothing but the amount of work done to move one coulomb of charge from one point to another. Okay, so now we have this. Now what we should do, we should just derive its formula. So for deriving its formula, what we need to do before deriving it, we will learn the SI unit of them. So SI unit of them is nothing but potential and potential difference. SI unit is nothing but watt. Okay, so SI unit is equal to volt. So now what we can do, now we will just derive its formula. So the amount of work done, before deriving its formula, let me explain it very easy. So the amount of work done, suppose there's a man over here, okay? Assume that there's a man over here trying to push this object from this point, from point A to the point B, okay? To the point B. Now what we should do, we should just count. So the watt will be equal to, so watt is equal to the amount of work done, how much work he's doing. For example, if he's doing 25 joules, let's see, okay? 25 joules of work done by, so the watt will be equal to 25, the work done by the amount of, to move 1 coulomb of charge. So suppose there are 5 coulombs over here. Okay, so he's moving this 5 coulombs inside the box. There are 5 coulombs. So he's moving this coulomb from one point to another. He's moving. Okay, he moved from here to here by using 20 joules of work. He used 20 joules to move this 5 coulombs. So the watt will be equal to 25 by how much coulomb he used. So it is nothing but, we'll get it as 5. So the watt is equal to 5. So what is the SI unit? So the formula is nothing but watt by equal to joules by nothing but coulomb. Okay, so coulomb is equal to V into J. Okay, now we have the formula for watt and potential difference. Now let's see the circuit diagrams. Now let's learn the circuit diagram. What is a circuit diagram? If we need to make some things, means if I need to connect a bulb with a battery and it should have a switch, means if I need to represent in a diagrammatic form, or I should represent and I should draw it in a paper, for example. If I need to draw it in a paper, what should I use? I cannot simply draw it in a realistic, like a wire like this and connecting to a bulb like that. So the bulbs, they can be in any types, right? So I cannot simply write a bulb like this realistic thing. Now some wire will be connected like this, and the switch will be also looking like the realistic switch like this. So our diagram is wrong if you draw like this. It should have a same, it should have, so if our diagram is like that, if you saw any other guy's diagram, it will be different. So it should be not like that. That's why they invented a circuit diagram. For making this thing itself, they made a a diagram for it only. So if I am drawing using the circuit diagram, my diagram will be same as my friend's diagram. So that is the thing. So now let's learn how to represent them for the different object. So first thing is nothing but the battery or the cell. Let's check how to represent a battery in a circuit. Okay. So battery in a circuit form will be nothing but there should be a positive and a negative thing in a battery, right? So a positive will be always be greater than the negative one. Okay. So this thing. Now we need to represent them whether they are positive or negative. There are two types like that we need to represent in the two types. Okay. So first thing is if the biggest one will be always the positive and the smallest one will be always the negative. And again what you should do plus and negative to show that it's in there's a power little. So next thing if I need to add two cell or two battery to it there should be one end should be always positive and the other end should be always the negative. So positive, negative, and again one positive, then negative. So positive over here and negative over here. So I have two cells in this. Second one is switch. Switch is as you know the functions of a switch. So switch can be written as a switch like this. So this states that the switch is off. So if the switch is off, how you can say, for example, there's a bulb over here, okay? Bulb over here and there's a battery connected over here and the switch should be there, okay? So the switch is over here. So the switch is over here means now the diagram isn't close. So the diagram, it doesn't allow it to flow the current. So the current will come like this and it will be stopping over here because it cannot fly like that, no? So it will just stop over there. So what happens? The bulb won't glow. So to glow it, what we need to do? We need to on the switch. So how it will look when it's on? When it's on, the switch will be nothing but there will be two dots in the line saying that it is connected, okay? Now let's draw a key. What is a key? If you ask, key is nothing but its principle is same as a switch. So, but it will be diagrammatically different, but its functions and it's very similar to a switch. So a key is nothing but, if I put up two brackets, this states that the key or the switch or the diagram is in a off. So the bulb won't glow. And to on this, what should I do? I should simply put a dot in between inside both the bracket stating that it's on. So the switch is on over here which allows the bulb to glow. So next one is what we'll have? We'll have the bulb. Okay. So how to represent a bulb? Okay, bulb, it's a universal bulb, means if you are drawing a bulb in a circuit diagram, it should be similar. Okay. So this is the way to draw a battery, a switch, a key, and a bulb also we should draw in the same way also. So bulb is nothing but draw a line, then draw an M like this and leave it and draw a circle around it. Okay. So you can see this is what you call a bulb. Okay. In scientifically this is how to represent a bulb. So next thing is ammeter. Ammeter. What is an ammeter? It's new, right? Ammeter is nothing but it's, if you look closely, it means ammeter. Ammeter. If you're telling that means we have heard this word before, but there won't be TER. As you have guessed it, it's nothing but an ampere. So there's a device to measure how much ampere we are giving. So ampere is the device used to measure ampere. It's called an ammeter. So if you need to represent it in a diagram, if they ask you if they want to read they will need the readings of the ampere means, what they will do, we should just write okay. Now we need to draw a circle and close the thing. Now we need to write here, it is ammeter, right? So what is the first letter over here is A, capital A, right? So we will write a capital A inside the circle and we'll put a positive and a negative. Now next thing what we need to do, a voltmeter. What is a voltmeter? You have guessed it, I guess, from the name voltmeter itself. Ammeter means it measures ampere. Voltmeter means it measures volt. So let's represent it in the diagram. Voltmeter is the same as ammeter, but instead of A we are going to put V and the positive and negative. So now we have learned the diagrams over here. Now let's see what is an Ohm's law. So what is an Ohm's law? According to Ohm's law, the volt across the end of a wire is directly proportional to the current flowing through it at a constant temperature. So Ohm, okay, the man or the scientist who's made this law, according to him, it's like the potential difference, the volt across the end of a wire. So suppose there's a wire like this. So think that this is a wire, okay. So the end of a wire, there will be a volt. So the volt at the end of a wire, so the volt over here at the end of the wire is directly proportional to the current flowing through it. So there's a current flowing through it like this. Okay, it's directly proportional. It's directly proportional to the current flowing through it at a constant temperature. So volt is directly proportional to the current. Okay, so now the volt is also equal to I into R. What is here R over here? R is nothing but the resistance. Resistance, I will be teaching about resistance and the two types of them at my next video. Okay, so resistance SI unit is nothing but ohm. So now we got volt is also equal to, so at the first, what is the definition for volt? This volt will be equal to joules into coulomb also, and volt is also equal to I into R. And we can derive for I also. I is equal to what? I is equal to Q by T, right? And another thing is I is also equal to volt by resistant. Volt by resistant. How I got volt by resistant? So V is equal to I into R. I into R. So when I transform this V over here, what happens? In place of I am taking this. So here listen, it's normal, right? So I will be equal to V by R. So we know the value, we found the value for them. So now let's end the section over here, because it will be, if I take too long, it will be a little boring. So let me meet you in my next video teaching what's a resistant and the two types of resistance. So bye. If you have any doubt under this chapter, you can comment below and I'll read them and I'll postpone a day for it and I'll explain all the topics whichever you want. Thank you.